begin a little bit about myself. So I've been building open source software for more than a decade now. I've been involved with, I helped create Miami, which is a 3D visualization package in 2001, and since has had many revisions and versions after that. I've also been involved with SciPy itself, and most recently we've been building a tool called SciPyCon.Ar, which is a fluid flow separation tool for smooth particle hydrodynamics. I'll probably talk about it a little bit more. I actually teach in IIT Bombay, Indian Institute of Technology, Bombay. I teach aerospace engineering, and I've been doing computational fluid dynamics for my research, which I've been doing for the last since 1988. And in 2011, I've been collaborating with Enthought, consulting, working on their open source tool as an external contributor. But in 2011, the CEO of Enthought, Eric Jones, was a good friend, and he said, hey, why don't you start an Enthought India office? So I took 2 years off from IIT Bombay, where I teach, and I started a Enthought India team. We have about 10 people working in Enthought. So we have the India office, and I've helped set that up. So let's get to the talk itself. The outline of my talk is basically, I'm going to show you an overview of what Enthought Tool Suite is. And then I'll actually take a small application and build it and show you how you can use ETS to build a little application with a scientific emphasis. Okay, so what is ETS? I don't have too many wordy slides about ETS. ETS is an open source tool suite, several libraries, several packages. We'll talk about the packages in detail, but the most important thing is they are all distributed under a BSD license, which means you can do anything you want. It is not commercial, it is completely free, it is not GPL, it is BSD. So the things you can do with ETS is you can build applications that look like this. So this is a screenshot of Miami, where you have a user interface embedded with 3D visualization over here, and an embedded IPython interpreter, and the ability to configure this and visualize your data in an integrated environment. Now the thing is, with ETS, you can build this yourself. And the hope is, at the end of this talk, I'll give you enough of a start that you can figure out how to build it yourself, things like this. The nice thing is, I'm not a computer scientist. Some people will argue that I know more than some people in computer science, but I'm not by training a computer scientist, and I'm not interested in necessarily or to build the UI by hand myself. So the ETS has a set of tools that allow to make it very easy for you to build your own kind of tools without getting into the nitty-gritty of actually laying out the user interface. The other nice thing is you can build customizations, like you can build your own widgets. For example, here you have 3D visualization on the left-hand side, and you have these sliders on the right-hand side, which if you drag, it will change the visualization of the fly. So you can build applications like this very easily. And things like this as well, where you can embed 3-dimensional and 2-dimensional plots on the same figure and interact with them. I'll show you a bunch of these demos as we go on. But the entire tool suite basically consists of the following packages. It consists of something called traits, which is a library. And then what you do is you write your object model in traits, and I'll show you examples. And then to describe or build a user interface, there's a library called traits UI, which lets you specify how your user interface should be. So it's entirely declarative. I mean, you don't have to write widgets, but you basically say, I want to see this element. Okay? And that element is something which is a trait. And using that, you basically build up the user interface. And then you have Chapo, which is used for 2D visualizations. It's kind of like Matplotlib. In fact, some parts of the API are similar, but Chapo emphasizes on a lot of interactive visualization. I'm not going to talk too much about Chapo today, but I'll show you how to get started. And then Maya itself, which is a 3D visualization library. And then you can build small things, little user interfaces, dialogues, create your object models using traits, UI, Chapo, and Maya. But if you want to put together a complicated and sophisticated application, you usually need need some framework that puts all of these together and allows other people to contribute to your application. So we also have something called Enthought, which is an application framework, and it's modeled closely on Eclipse. The kind of approach that we use is similar to that. So you have plugins, and Enthought basically allows you to build applications that are composed of plugins, which have extension. So how many of you know Eclipse? And apart from this, there are a bunch of miscellaneous libraries. So all of this together, and a bit more that I have not discussed, form ETLs. So if you look at it graphically, you basically have Python at the lowest level. You have traits on top of that, and traits UI. And traits UI allows you to either render it with a Qt or WX Python package. So you don't have to worry about which package you use. It works with both. And on top of that, you have Enthought. And you have Chapo, which depends on traits UI and a bunch of other libraries. And then Maya is kind of on the top, which depends on Enthought, traits UI, traits, and it uses the external libraries on the left. All the ones in red are external libraries. So let's get started. It's a lot more fun to actually get building an application. So what are traits? So how many of you are familiar with Python classes? Creating an class with Python. Or objects in general? Okay, more of them. Okay. So basically, when you create a class, you can construct instances of that class, typically called objects. You put these objects together and have them interact. Right? So Python objects typically have attributes. Right? And a trait is basically a special kind of attribute. Right? So it has special properties. We can see what it is. So here's a simple traits example. So I'll walk through this. So the first line is an import, which basically imports a class called as traits and range, enum, and str, etc. So look at the example. It says class person as traits. The name. So in this case, if you're a traditional Python programmer, you think name is a class attribute. It's not. In this case, when you say name is str, how many of you have written Django code? Okay, so it's similar to how you create a Django model, right? So when you say name is str, it's not a class attribute. You're basically saying every time I create a person instance, right here, the name of that individual person is supposed to be a string. That's all it's saying. Okay? The sex of the person is an enum, which is either female or male, and the weight is something between 0 and 300. So each of these basically declares that attribute has certain properties. Right? So the other thing you can do is, so the instant you define them as a range, so supposing I set the weight of this person to -1, it will tell me it's an error. The weight has to be between 0 and 300. Is this clear? Or if I assign the number 1 to the person's name, it will be an error. So maybe I'll switch to. So here's the example. I'm just going to run it. Is the font visible? So the same exact example. Comment this out. Okay, so if I go p.name, it says Joe. Right, so if I do p.name is 1, it's actually raising an exception saying the name trait of a person instance must be a string, but a value of 1 was given to me instead. Okay? So it gives you type checking on Python attributes, which is something we don't have with vanilla. The other nice thing about this is whenever the weight changes, right, I've defined a handler for weight change. So every time the weight attribute changes, it will run this code. So let's try it. So p.weight is 0 currently. I can say p.weight is 100. And it basically said what's your weight weight. Right? So now if I reduce it to say 75, we won't print anything, go back to 100, it's going to say. Notice if I did p.weight is 100 again, it doesn't call it because the weight hasn't changed. You may have assigned it, the weight did change. So it's smarter. So this is all very nice. The cool thing for a scientist who's not concerned about creating a user interface is I can now go p.config.traits and I have this cheap user interface which has a slider, and if I increase 80, notice that if I change something on the UI, it's printing out, it's reactive. So for example, if I say name, notice that the UI also responds to. Okay? So I can, this is very easy to do. I didn't do anything to build this user interface. I didn't create a Qt object, I didn't create a WXPython object. It's completely transparent. So this is a nice feature of traits. So we call this visualization. So you have Python attributes that can be type checked, that have a visualization that comes for you automatically, that also have notification. So if I change an attribute somewhere, you can catch a notification. So you could even create a function and then say, whenever that trait changes, call this function. So maybe you're going to do that. So there. So let me say. So now if I say p.name is a printed name. Okay? So I have notifications and I can pop up visualizations with these attributes. So traits form the cornerstone of ETS. So you can basically build up powerful objects that react, that do things that you can easily pop up visualizations for using traits. Now traits UI sits on top of this. In this case it was transparent. It automatically looked at my object, figured out what are the traits, created visualizations of those. So what this forces you to do is it forces you to create objects and focus on the object model. Notice I didn't worry about should I use a dialog, should I use a button, should I use a menu, should I do this, none of that nonsense. I focus on creating an object model that's clean, kind of like Django's objects. Right? You don't worry about views. So you can basically create without even forcing yourself to learn MVC. How many of you know MVC? What MVC stands for? Okay, about half. The rest of you don't know what an MVC is. So MVC is basically model view control. So you build objects so that you focus, you write your model separately, you write your view separately, you write your control separately. Now you don't have to do that. Here you just focus on writing the model, and the views actually are separate from your model. So the nice thing that you've seen is you can create default views. You can create multiple views that are synced to the same model, right? So on the IPython interface, I could say p.weight. On the UI, I can change the weight. They're all synced up. You don't have to worry about coordinating between these various pieces. Now, the default UI you might not like, right? So you might say, hey, you know what? I don't want the name to be at the top, right? So using traits UI. So if I just add this to my code, which basically says view is, I want the name to be first, and then I want this X, and then I want the weight. Okay, if I want this particular order, then I run it this way, I'm going to get the weight at the bottom, unlike the previous case. So you can use this declarative approach to say how my layout should be, what should be the title of the video. So that's the basics of traits. So now let's pick an interesting problem to solve and start building a little object model around it, along with the user interface. So let's solve the Lorentz equations. How many of you have heard of this equation? Okay. So this is a very fascinating equation. We won't get down the equation itself. So this is what you call an ordinary differential equation. And it was the first equation that was identified in the literature that exhibited chaotic behavior, what we come to know as entire field of chaos, which has come about, started with this paper published by Lawrence. But ultimately, it's just a set of three coupled ordinary differential equations, and you have to integrate it to obtain solutions. So if you want to think about it, you can think about it as dx by dt looks like velocity in the x direction, dy by dt is like velocity in the y direction, and dy by dt is dz by dt is in the z direction. So if you think of a space, of say this room, at each point if I assign a coordinate, this basically specifies the x, y, and z velocity. Right? So now if I have say a particle of a piece of dust here, how does this dust evolve in time is the real question you're asking. So if I solve this problem, I'm basically saying given a piece of dust here, if I start at t equals 0, at 10 seconds from now, where is this? How does this particle move in time? Is basically what you're asking. So to solve this with straightforward NumPy and SciPy that you already looked at, it's very straightforward. Import NumPy, import SciPy's integrate has an ODE int, which basically will integrate this vector field for you. We first define a function called Lorentz. It takes the following arguments. X is the position of this point in space, x, y, z. It's a triplet. T is the current time. S, R, and B are basically these parameters here. Okay? So here's a simple function which actually returns the right hand side of this differential equation. So this is the right hand side. Okay, is everyone with me? Okay, cool. So all this guy is doing is he's evaluating the right hand side and returning another NumPy array, which is UV and W to the right hand side. So to solve this, basically the start is the initial point in space. And you're saying at these times, 0 to 50 seconds, give me 2000 points in free space, integrate the Lorentz equation from that start given these lines. Okay? And then with these two lines I can plot it in biology. So let's look at that. This is the same code, nothing has changed. So let me run it. And there's my trajectory. Okay? As you can see, it's a beautiful trajectory. Okay? So great, we have a solution. That's nice. So now I want to do something nicer. I'd like to be able to say, what happens if I change the initial point? What do I have to do now? I have to go back to the code, change the start value, or change, if I want to change S or R, I have to change those parameters. So I have to go in the code and change. Now I want to build a user interface, which has this, which has sliders, where I can click, drag, move things around, and the UI automatically updates. Right? I'd like to do that. So let's see how we can do that with traits. So we start at a low level. We'll first build an object model. So I first declare a class called ordinary differential equation, which has, so I just declare, I'm now declaring an API. Every ordinary differential equation has a right hand side, which takes two arguments, x and t. X is the current value, the current state of the ordinary differential equation, t is the current time. And in this case, it's not implemented anywhere. This is just an API. So now for the Lorentz equation, I want S, R, and B, these parameters to be sliders, which are parameters that the user is interested in. I'm not even thinking sliders. These are parameters that should be between say 0 and 20, 0 and 50, 0 and 10. Right? With defaults as 10, 28, and 8 by 3. Right? This is my RHS. So this object, this class imports the Lorentz equation completely. Is this clear? And now I create a solver which basically says it has an ODE which is an instance of ODE. So this is a new trait, instance trait. So when you say something is an instance, it basically makes sure that it's actually an instance of that class. So any subclass of ODE or ODE itself is accepted. Anything is not, it will raise an exception, saying trait error. It expected this instance, but you gave me that instance. And then we have an initial state, which is an NumPy array. And you have t, which is the values of time at which you are seeking the solution, which is also an array. solution has to be computed, right? So anything that's typically a computed quantity in Python is usually a property, right? So traits also have this property trait, where you're saying this property is an array. Am I making sense? Too fast? No. Not making sense. I'm making sense. And this trait, this property, depends on the initial state, the time, and the ordinary differential. So is this clear? I mean, verbally what I'm saying is very clear, right? My code is saying exactly the same thing. The trait solution is a property. The property is actually an array. It's going to be something computed, it's going to be returning something. And it depends on the initial state, t, and on. And then some code. The get solution must be familiar to all of you who have ever written a property. Get solution is basically the method that computes that solution and returns it. So it simply says return self.solve. And there's a decorator here saying cached property. Now the issue is, supposing I don't change the parameters. Every time I do get solution, it should be recomputed, right? See, an ordinary differential equation might be complicated. It might take a lot of time to evaluate. So if I don't change any of the parameters, I don't want to recompute the solution, right? So what this does is this cached property will make sure that if the parameters haven't changed, that is, any of the dependencies, initial state t or the ODE have not changed, it will not recompute the solution. Okay? So basically cached solution. Only if the dependency is changed will it recompute. The solve is simply doing what we did over here. It's doing ODE int. So it's importing ODE int and then saying ODE int, the ordinary differential equations right hand side with the initial state and then time. Okay? And then the ODE is Lorentz equation, solver is blah, and I can now ask solver.solution for everything that I have just done. So let's look at that. So here is how I'd use this. ODE is Lorentz equation, solver is ODE solver, set the ODE, initial state is 1, 1, 1, T is 1, 2, 3. So the values of 1, 2, and 3 give me the solution. Print solver.solution. So let's look at it. Okay, so I first printed solution is solver solution. That's the first value you get here. Okay, and then I change the initial state and I get the next solution here. Okay, but then I change ODE's parameter S. Right? The solution didn't change. Do you see the problem? So I'll go back, show you the code. And show it right here. So I have the Lorentz equation which has 3 parameters, S, R, and T, has an RHS. And I have the ODE solver which basically has the solution which depends on initial state T and ODE. And now when I changed the S of the ODE, it didn't recompute the solution. Why not? Because the dependencies depend on initial state T and the ODE. So only if I change the instance of the ODE does it actually. So if I create a new ODE and pass it in, it will recompute. But if the ODE's internal properties change, it has no way of knowing that. Okay? So to handle that, we need to do a little more work. So what we do is we can create a trait called an event. So now I can say, whenever in the Lorentz equation, if R, S, and B change, I'll fire a changed event. Okay? And then in my ODE solver, I simply say ODE.changed is all I need to listen for. Now this will handle 2 cases. It will handle the change if I actually change the ODE, that is if I create a new instance of the ODE and pass it, or if the ODE's changed event is fired here. Okay? So is that clear? So the issue was, if I change S on ODE on the Lorentz equation, the ODE solver has no way of knowing that S changed. right? It's not listening to every single attribute change of that object. So I need to manually wire it up to say when S, R, and B change, you make sure that the OD is changing, right? And so the event trait lets you hook those things up. So let's run that. So again, all I've done here is, this is the Lorentz equation. All of this is the same code. Change is just a new event. And every time any of these traits change, that's a decorator which basically says, if S, R, and B change, fire the event. And now let's run the same example. Notice that it changed. This value is different from this one. Great. So now we have an object model, no user interface. We have something where I have an ordinary differential equation. I can change parameters. I have it all hooked up nicely so that if I change some parameter on the ODE, the solver will automatically update. I get solutions that are cached, so I don't recompute a solution if nothing has changed. Okay, so all nice. Now I'll build a UI. Easy. I simply create a view and say, I want to see the ODE, the object, the ODE object, and I want it to be a custom style so that I can see all the attributes of that ODE embedded in the UI. I want to change the initial state, and I want the solution, but I'm not going to write the solution, right? So I'm going to make it read only the solution. And I want this item. So now let's. So that's the code. The only addition is these 5 lines. Now let's run this. So now I have a cheap looking user interface. So now the nice thing is, if I change this, the solution updates. If I edit this and say 10, 100, 1, it'll update and change. So I've now built this minimal user interface, which can just at least print the solution out in a fashion that I can use. And I didn't write any Qt code, I didn't write any WXPython code, and this will actually work on both. All we did was we wired up changes using the onTrade change decorator. We used depends on. So we created a property, the property depends on other traits. And then we used an event trait so that we hooked up any changes to S, R, and B to the ODE solver. Okay? So now let's get a little more interesting. Let's build a plot. So now I create another plotter. So I say ODE plot in 3D. And now I create a plot instance, a solver. And I say that's the view. I want to be able to view everything about that solver. Right? And whenever the solver's solution changes, I want to plot. So I basically, first time when I run this solver, there is no plot. Right? So plot will be by default none. And I first time when I plotted, I say my mlab.plot3d, R0, R1, and R2. Is this clear? So the first time I'm running the same that one line of code that we had when I wrote that initial piece of code. Is this clear? Right? So now all I'm doing is, if the plot is already there, I'm just updating the data. So I'm just getting the existing plot, saying p.mlab source.reset x, y, z, and set all of that. So that it doesn't create a new window every time. It's just updating the data. Similar to matplotlib's set data function. Same thing. So let's run this. So again, the same code, there's no magic. I haven't changed anything special here. Now let's run this. And there we go. There's my Miami plot, and this is my little UI. And now it automatically updates. I can change the initial condition. specified view, and I'm done. Right? But this is still a little clunky, right? I have one plot, I have my plot, I'd like to be able to build them together, right? So it's the next level that I want to do. And so this is like 73 lines of code. All of this to actually create a user interface with this. So now I want to be able to do the following. I want to create an integrated dialog which has the dials and the Miami plot embedded in the same thing. I'd also like to be able to do 2D plots. Right? 3D is fine. What if I have a 6-dimensional ordinate picture? I want to be able to look at each of those. I want to do all of them. And by the way, so I just showed you one plot in Maya. So you can imagine a more complicated situation where you have a very more sophisticated visualization you want to construct. Right? So this is just a simple example. So you can, Maya has the functionality to do contours, to do streamlines, to do a bunch of different visualizations. So you can do all of them. So to do 2D plotting, Enthought Tool Suite provides a built-in package called Chaco, which is very versatile. It supports and is built on top of traits. So now you can see why traits are a big deal for Enthought. As in, if I have some object that has traits, I can put things up very easily. I don't have to write too much code. And if something changes, I can have it propagate changes to something else. So Chaco is basically built on top of traits. You can embed the graphs that you generate on objects by the and Qt, which means if you have an existing Qt app, you can embed Chaco. It produces fast and interactive visualization. So Matplotlib is very geared towards publication quality plots. But interactivity wise, Chaco is usually a lot better. Functionality is a lot. So you can make the usual set of plots that Matplotlib can. So here are some simple demonstrations. I'm not showing these as demos right now. But on this plot, for example, as you hover, if you move your mouse cursor, the plots there will automatically update. Right? So you can build very rich visualizations with Chaco. I'm not going to show you that. So now let's build. So if you recall the code that I wrote for the 3D visualization, I had the Lorentz equation, I had the ODE solver, I had ODE 3D plot. So like that, I'll create an ODE 2D plot. So I have an ODE plot over here, which has an instance of solver. Maybe I'll just show you the ODE 3D code first. So ODE plot 3D had the following. It had a plot, which is something that Miami returns. It has a solver instance as a view, and it sets up how the plot is generated. Now what we're doing now is a little more complicated because I want the whole thing embedded in the same user interface. I have a solver instance just like before. But then I have a plot which is an instance of component. Now Chaco objects are all enabled components. So for now don't worry about what enable is and all that. Think of this as a recipe. I have a plot which is an instance of a component. And I have this plot data which basically marshals the arrays that you want to plot. Think of it as again a Chaco specific detail. And I'm able to plot x, y. So remember there are 3 components to the solution. So we're solving the Lorentz equation which has 3 components, x, y, and z. Right? I would like to plot any of these. So I want to be able to plot that. So here is an array component that I want to display. And then you set up the view. This is just as before. So if you notice in the ODE 3D plot, I again had an item solver. Right? All I've done is I've added this group, which is the array component, and this plot, which is the only special thing here, which is basically going to edit this component editor. Right? So all I've done is I've created a plot object, and I have to tell the traits this UI piece, how to render that widget, what to render this 2D plot. For that, I simply say the editor as a component, right? And then I set up the plot. So I say whenever the solver solution changes or the array component changes, set up the plot data as time, grab it from the solver, set it. This is just a simple mapping from axis of x, y, and z to indices of the array. Grab the solution and set the value of the solution to the third column, right? So when ODE returns, it gives me 3 columns, x, y, and z, for all of those t values. So I'm just getting that and setting it. So I just basically have x versus y plots. So the other thing here is I'm going to use 2 pieces here. One is all of the Chapo pieces, which is the instance, component, and the component editor. Right? That's really the only new pieces here. Now, the first time the object is created, this magic method plot default will set up the plot the first time. Okay? So what it does is, it creates a plot object and sets up to plot t versus the value. Okay? And then you'll end up with something like this. Let me show you the code. So there you go. As before, it reacts. I can interact with this plot. I can change the initial condition. I can change the array component. If I wanted, I could plot all of them in the same plot, right? I could plot one with red, one with blue, one with green, show a legend. I could have done that. This is just showing you an illustration of what you can do. So, for example, this is Z. What happens if I change any of these parameters? So I can do this very easily. And the code to do it is essentially this 78 or 15 lines of code to generate this plotting piece. So if you want to do the same thing with Maya, you want to embed it, the idea is similar. Okay? So again, here's an ODE plot 3D. The only difference is there in the previous case I had this plot. Here I have a scene and a plot. The scene is the actual embedded visualization, and the plot itself, the thing that's being plotted. And when I edit the scene object, I say use the scene edit. So the pattern is the following. Every time you have a trait that you're trying to visualize, so over here solver is an instance, is an object, right? That object defines its own view. So it automatically picks up and embeds that view here. In this case, it doesn't know how to edit this scene, and there's a scene editor which knows how to do that. You're basically saying edit that with the scene editor, which knows how to create the UI, the plot, and all that stuff. And then you hook up the views. So you basically say whenever the solution changes, and this is the same code. If self.plot, self.plot.envelope source, set, x is x, y is y, z is z. And the other thing you do here is, the first time when the plot comes up, you say create the first plot. That's it. So in previous case you had plot default, which the first time the object is created does it this way. In this case, you do it only when the scene is activated. This is for technical reasons because Maya is using OpenGL. It needs to set up an OpenGL context, and that only is set up when you open the window. So there's a trait that's fired called scene activated, which is when the window comes up, and at that time it will set up this. Right? But the ideas are very, very simple. And remember that I have not touched any of my object model. My ODE solver is untouched. My ODE solver is untouched, my ordinary differential equation is untouched. I have now created a class that manages this view. and you end up with something that looks like this. The same thing here. Same thing, but now I have an embedded visualization. Okay, and of course this is all Mayavi, so I can click on that, change some of the properties if I want to. So if I say variable in the background, I will make it white. I have all the abilities of Mayavi itself, but it's all embedded, and it looks like I've created this application tailor-made to solve ordinary differential equations. Now, obviously, in this case, this ordinary differential equation has these options, right? This SR and P. Now, you can imagine creating a more sophisticated system where I can have, say, a family of ordinary differential equations. And each time you should have a drop box which says Lorentz equation, some other equation, yet another equation, all of those. You drop them down, you change that, it will automatically change the user interface, then you will have those UI elements and then corresponding visualization. So you can basically hook it up in very, very rich ways. So the interesting thing is, so if you look at the Mayavi code base itself, a lot of it is based, most of it is actually written in traits. So all of the dialogues you actually see on the Mayavi window are typically automatically generated from traits. Not written in Qt or WX method. Very minimal Qt WX method code, but the actual Mayavi object interface does not create explicit UI. So the nice thing that does is, when I am programming, I don't have to worry about the UI, how am I going to structure the UI, none of that. I have to worry about the structure of the UI, kind of like HTML. I don't have to worry about the CSS parts or the Ajax parts. All I do is create a pretty clean object model, and the rest of it is kind of automatic. So with just these pieces, you can start creating rich objects that interact in interesting ways. Another 10 minutes, 5 minutes. So I won't spend too much time on envisage itself, but so using just these pieces like traits UI, Chapo and Mayavi, you can now imagine you can create a fairly complicated user interface. You can build up all kinds of interesting problems. You can solve a suite of problems with that. But all of these can be like a small dialogue kind of interface. Suppose you want to build a full-fledged application. I want the application to be customizable. I want it to be extensible so that I'd like to be able to have plugins, say. And that plugin should be able to configure the application. Different plugins should be able to collaborate. Right? So to do that, you need something more sophisticated like an application framework. So Envisage basically provides this. So what it lets you do is, you as a developer, for example, in Mayavi, what we did was we created the object model, didn't worry about how it's going to talk to other applications, all of that. Create all of that, create the objects, worry about the UI and how it's supposed to look in terms of traits. So we focus on building a clean, scriptable, testable API. Right? A clean library. Right? And the framework then specifies how you're going to interface your library with other pieces and the actual application. So to do that, you basically expose your library in the form of a plugin. Right? And the application writer will start using different methods to compose an application. So every Envisage application basically consists of a set of plugins that are put together. Right? And each plugin will contribute some what are called extension points to which other plugins can contribute items. So for example, if you have a message of the day, the one plugin may make a message. Right? It will have a queue of messages that other plugins can contribute. So supposing you say, both of button message of the days. So you have a list of messages that you want to contribute. So you create a plugin which will basically have return a list of whatever contributions you have. So the application now loads your plugin to just contribute all of those stuff. So the application now sees your contributions in addition to what is there in the plugin. So each plugin, as I said, defines extension points, and extensions will be contributed into these extensions. So if I have a message of the day application, we have a message of the day plugin which receives extension points called messages, and other plugins will contribute to this. So basically it looks something like this. You have a message application, it has an extension registry. The extension registry is a set of, in this case, it basically is a set of strings, which basically says, so messages will be an extension registry point, and it will be a list of various extensions that people can contribute. And other plugins will contribute either extensions to various plugins, or they'll offer services, which are objects that are constructed. So you can basically compose an application which each offers a set of services and extension points. So together you can build up a fairly sophisticated application. So I'm going to stop here because envisage is, even when I explain it, it's not that easy to sort of grok an application framework. You basically write one. It's much easier if you take an example, a simple example, and start building up. And usually it doesn't go very well. So I very specifically not delved into the message itself. We don't have enough time to really go into that. But the point is, you can really build large-scale applications, which do fairly sophisticated things. So all of our commercial offerings, what Enthought does, typically we use all of the Enthought Tool Suite, the open source toolkit, and on top of that, we build applications. And so we use a message heavily. So the idea is you put together sophisticated applications and you plug them in together. That takes a lot more work and a lot more thought, but the end result is you can have very reusable pieces that you can easily bundle together and build a very rich application. So those of you who use Eclipse, I think will have a sense of this, because Eclipse is not really an IDE. Right? How many of you think Eclipse is only an IDE? Everybody seems to know that. So Eclipse provides, you can build not just IDEs with Eclipse. That's kind of the point. So in summary, if you kind of learn traits UI, Chaco and Mapping, initially it looks very daunting because it's a huge set of tools, a lot of new things. But once you learn it and start building it, you get very rapidly, you can build very powerful user interfaces. So the app I was using to demonstrate all of the demos is Canopy, which is something again which uses Enthought Tool Suite heavily. It's available for free, and for academics it's completely free. You can download it if you want. Thank you. So you're saying if an exception is thrown in a trait handler? Yes. So yeah, so the callee is going to give the exception. So it will propagate all the way back. It's basically so if it's a trait handler, that's called when you set a trait, and that down the line changes somewhere and cause an exception, you'll see that kind of value as soon as you set that trait. But if you're doing threads and stuff, then it's, of course, it's going to be weird. Right? So I have another thread firing this thread is going to see the exception. You need to be a little careful. One of the things you need to be careful with UIs and threads. Yeah. say dependencies in terms of installation, install time dependencies? Okay, yeah. So you may say with envisage? With envisage? Yeah, so with envisage what you can do is, I mean there are, I think Airbus for example has a large scale application. So you can build a basic application which you can have an installer for, say the SI or a DSG or Tata. And so there are two ways, right? You can install it either as a self-contained application, in which case you will freeze the application using PyInstaller or something. But if, let's say you have a Python environment, I have a Python installation, and you install, say, Miami, right? Miami is an application which is built using Envisage. Now, if you have extension points, you have a plugin. If you install the plugin in the same Python environment, it will see it. So, for example, if you look at nose, right? Nose can be extended with plugins. The idea is the same. You basically install the egg inside your environment. You can use package resources to query what are all the installed eggs that provide a particular extension. And then you can grab those and extend it. Yeah, you can freeze it, but it's a headache. I mean, freezing is not easy, right? It's a freezing an application, a large scale application is not. I mean, you have to use, even if you use PyInstaller, for example, which is what I used to use long ago, you have to basically make sure exactly that you don't run into the situation that you have libraries that you depend on. So in this case, you make sure you bundle those as well. So yeah, so that's a tricky issue. But if you have a Python environment already, so if you have the user has a Python install, and you install this as an egg or just a routine, quick install, and then it should be able to pick up any eggs that have been installed by the user maker. You can basically, so for example, if you look at a setup.py as an entry points, right? So you can declare entry points saying, here are my envisage.plugin entry points. And envisage plugin loader will look for those extensions, those contributions, and then load those points. So you can do that. So for example, in the Airbus, that's already good. You basically, any eggs that install will add a contribution, will add an entry point in setup.py and says envisage plugins, blah, 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 blah. And then it will load each of those and start the application with those plugins. But then you need to worry about when your plugin crashed or something. That's a different story. But basically, that's what it is. Anything else?
Yes, so this is not a very good question. So you make say program or company. So I don't know what company you make program for.
So the question is, what companies does Enthought make? So, okay, so as an open source developer, you can make any number of these. But Enthought itself, we have a large number of clients. We have clients in the financial industry. We have a lot of the visualization, the 3D visualization especially is done for geophysicists. So if you're doing geophysics, you basically, and oil, people who cut for oil, basically they, so if you look at the earth, they basically send solar things down, look at the reflection, and basically tell you what is the materials inside. And now, the geophysicists will want to look at that whole cube and figure out where the oil is, or where should they drill. So for that, they require 3D visualization. They require, and a lot of them would like to use Python because I want to do some algorithm, I want to analyze some region, and in that region I want to run some algorithm. So you typically use Python in that space, and then you want to be able to visualize that. So we use, I think, Chapo heavily for, they have these things called log plots, which basically tell you along the well, what is the data. So it's called a well log. So we use Chapo plots, some of those extensions to the Chapo plots. And Miami is used for visualizations. That's one example. I think Airbus uses it for their wing design. they have an application, in-house application. Enthought didn't build it, but they use the ETS, heavily used Enthought Tool Suite.
Previously, Enthought was releasing EPD and ETS. Now, it's Canopy. Is Canopy going to replace EPD?
Okay, so question is, previously Enthought was releasing EPD, which is the Enthought Python distribution, which is like this. It's just a Python distribution. And now we have this thing called Canopy, which is also a UI and the Python distribution. So to answer your question, the question is are we no longer going to ship EPD? The answer is yes, the future is we're going to be shipping Canopy. Canopy itself is based off of EPD. It's basically, it is a full-fledged Python distribution. It supports virtual environments, so you can basically create any number of virtual environments. It supports it cleanly. And it provides a UI, which is optional. The thing is, since Canopy 1 release, we haven't made the headless, the no UI case hasn't been made easy to use. So that will come out in the next 6 months. Where we make it easy so that you don't have to actually fire up the user interface or use the UI, but you can use it as just a Python distribution. It's going to happen, but the answer is no. Canopy is the future of EPD. EPD is no longer going to be a separate piece. You can download the old versions. So if you go to the download page, there's a little link there in EPD. But we are not going that direction of just EPD. It's going to be Canopy moving forward. Yes, please.
Is there a browser-based implementation of Trace UI?
Good question. We don't have one right now. There is an experimental one that was based on, I think, a SQL algorithm internally. I don't think it's ever been released. And some of the people basically think it's not, doesn't make as much sense. Because most of Enthought's own internal needs are for desktop applications. However, archaic it may seem, a lot of these people who use applications in the industry are not very web heavy. They don't imagine if I have a cube which is a gigabyte large, they want to analyze that. The web isn't really the domain to really play with that data. So we haven't yet done it, but the ETS, I've not talked about it. The ETS has one library called Enamel, which does support somewhat HTML5 based backend, but it's not very certain where that is going to go in the next 6 months. It's evolving, the API is changing, it's not very clear. But we don't, to answer out and out, we don't yet have something which is a web-based front-end. But I don't think in theory it should be too hard to build on. The issue is more of how do you make it work? The problem is it's a different paradigm, right? You have to think very differently if you're starting to do something which is disconnected, the model living on some other location, or either on the server side, and then being able to display that information. So that I think has to be thought through a little bit more. Okay. Thank you very much. I'm